do this. Morning, Foxy Kens. Morning, Gotham. Let's close. I didn't close all this stuff. Okay. Let's do this. We got lecture 5. Linked lists. So our goal is programming test 3. This is what we're working towards. And it's not going to be till one of the last examples that I'll have an example that pretty much fairly one-to-one correlates with this objective, at least the setup of it. And for objective 3, you're going to add a linked list to the song class, and that linked list is going to store your ratings. So we want a linked list of ratings, and we're going to use the linked list node class that's provided in the handout for the homework. So ratings.datastructures.linkedListNode, it's been there ever since you cloned the repo for task 1. Use that class as your linked list node class. Don't create your own class and your own package or anything. Do not use the internal Java linked list. I see way too many students who do that. It's nothing I'll ever talk about in lecture, but some students just decide to use that, and then they wonder why their homework doesn't work. It's because you did the wrong thing. I shouldn't say that so dismissive. I say that because, again, I suspect that they're up to nefarious things when I see that, because they clearly ignored lecture. Maybe sometimes it's a simple mistake, but it's hard to believe that. Okay, so once we have the linked list as part of the song class, and it should be an instance variable. I think I spoiled that right in here also. That should be an instance variable in the song class, and we have various methods that will interact with that linked list. Add rating to append to the end of the linked list a new rating. Get ratings, which just returns the head of the linked list. Set ratings, which sets the head of the linked list, so a getter and setter. Those should be straightforward. What's up, Bonnie Boy? Average ratings, which will give us the average of all of the ratings in the linked list, while ignoring invalid ratings. So any rating with -1 should be ignored completely, as in don't have this as like 6 divided by 4 or 4 divided by 4 or anything. It should be 6 divided by 2, because there are only 2 actual ratings, and they're 1 and 5. So the sum of 1 and 5 divided by 2, 3.0, should be your expected there. And aside from ignoring negative ratings, ignoring these -1 ratings, these invalid ratings, which isn't overly difficult, but aside from that, all of these methods here should be straightforward. Pretty straightforward to test, pretty straightforward to actually don't ask you to test them at all. You have to test average rating and remove rating by reviewer methods only. You don't have to test your getters and setters. I'll test your getters and setters, so if you do have a bug there, but they're getters and setters. Add ratings, sometimes students have bugs in add rating, because you do have to do a little bit of work there, but there really shouldn't be bugs there. I have seen students doing more work than they have to usually. And I'll explain that in lecture when we get to the relevant points. Like, add rating should be a very straightforward method, because you can use a lot of what I show you in lecture, pretty much just cut and paste my code. But all these should be pretty easy. Where the challenge comes in for this assignment, and where you'll probably spend most of your time, is remove rating by reviewer. I'm not going to show you any one-to-one how to do this in lecture. I'm going to show you the theory behind it, and you have to decide how to turn that into code. So remove ratings by reviewer. This is where all the bugs, office hour questions, Piazza questions, this is where everything is going to be, is remove rating by reviewer, or at least most of it. I mean, there are going to be other bugs, especially in average rating. The average rating isn't trivial, but especially since it's your first linked list algorithm that you'll implement. But remove ratings by reviewer. This one gets a little bit tricky. Not super difficult compared to what's up ahead of us in the later tasks, but I would say, in my opinion, this is the first actual challenge of the course, is getting this remove rating by reviewer method implemented. So if you've cruised through task 1 and task 2, fantastic. I love to see that. Don't get too overconfident quite yet. You can get overconfident when you get through probably test 4. That's where you can say, I got this. But this is going to be your first big challenge. So don't go into test 3 treating it like it's going to be as easy as tests 1 and 2. So there's your fair warning for that. And one thing that we'll see, and I'll try to mention throughout lecture today, is null pointer exceptions. Pretty much every question, almost all, I'd say 90% of the questions on test 3 are, what the hell is this null pointer exception? Why am I getting this in AutoLab? And there's going to be a few reasons for that. One, a lot of what I see is students writing their code first, write their code and then their tests and then their testing utilities, and then there's a null pointer exception in their code which they weren't expected to even have written yet before they check their testing utility method in AutoLab. And AutoLab will say, checking your testing utility method, I found a null pointer exception and everything crashes. And it makes it look like the error's in your testing utilities utility method, which is compares two linked lists rating. Oh yeah, I forgot. This one's fairly challenging too, comparing two lists of ratings. Not overly challenging, not nearly as much as removing rating, but it does have its own challenges. So it makes it look like the error's here, but whenever I look at the code, it's because there's an error here, but they never finished their testing utility method. Like, you should do testing utilities, then testing requirements, then programming requirements in that order, and get your feedback from AutoLab. Make sure AutoLab checks you off on each one in succession before starting the next one. That's the intent. That's the intended way to handle this. And then for your methods, you stub them out. Just have them return some default values and not implement them until later. So if you do see that null pointer exception and you did write your code before getting checked off on your testing utilities, that null pointer exception can be anywhere. You probably wrote a bug in your methods themselves, and it's breaking your testing utility. It's showing in AutoLab as just broken during the testing utilities because it broke sometime after that. So just a heads up on that. I'll still get that question a bunch because it is a little confusing. If you do things out of order that AutoLab's not expecting, AutoLab does get a little confused on that one. So there's your warning on that one. Let's get into some slides. Download all 3 of these. And we gonna get through some slides. Okay, I should give a quick update. We just had the test 2 late deadline. I saw most of you hit that one, and I'm sure anyone who's here live has met that expected deadline. I'd be surprised if anyone who's here live didn't make that. So there's no point saying that just for people who are watching the VOD, because when they're watching the VOD, they're probably several deadlines later, and they're a lot of them, unless they're watching it today on Tuesday the 11th. If you're watching it after the 11th, you're probably failing the course anyway, just to be blunt about it. Is there much live coding today? No, I don't have any live coding in this lecture. Again, in the 11 a.m. lecture, in the second lecture, it'll be all live coding. In the 8 a.m. lecture, this lecture, it's going to be all slides, especially today. Sometimes there's live coding in these lectures, just a little bit. Today, there's none. And the test 3 expected deadline is going to be 2 days, as always, Thursday morning. That's when test 3 should be done. Let's close these ones, and let's full screen this one. Start going through some linked lists. So if you want the live coding version of this lecture, 11 a.m. to 1 p.m., 1:30 p.m. Eastern. That's when that's going to happen. Okay. So let's get into it. It feels the gap between the Thursday and Tuesday lectures feels good, but got to adjust back into things. And just a reminder, the way I'm treating this course and the way I recommend you treat this course and the way the structure is set up and everything is to treat this as a 4-day week. So we have Monday and Tuesday where you're doing test 3 this week, and then Thursday, Friday, where you're doing task 4 this week, and then a 3-day weekend, Saturday, Sunday, Monday, to relax, regroup, and then get back at it for another 4-day burst. That's the intent of, the way the course is structured. So, all right, let's get into it. With the expected deadlines, I should say. The expected deadlines are strongly encouraging that, pushing you towards that. So sequential, I'm just reading the first word I look at. So before we talk about linked lists, let's talk about array lists and arrays a little bit. This will be specifically about arrays. Array lists hides the underlying array, as we saw, and gives us more functionality on top of that. But this is how the concept of arrays works. And let's review this just for comparison. We talked about it very briefly before, so I'll give just a little bit more detail, but this is a CSE116 topic to really get into the weeds and the details about this. They'll explain everything you've ever wanted to know about these things, and a lot of things that you didn't even want to know. So they are one continuous block of memory. It's a sequential data structure, and linked list is also going to be a sequential data structure, meaning order matters. But the difference is that an array is one continuous block of memory. It's one chunk of memory. When we create an array, we go to our operating system, we ask for memory in the heap, and we ask for one big chunk of memory that's going to store all of our values. And what we get in return is the memory address of the very first value in that array. We get that memory address. That's the reference that we store. And then we can do some pointer arithmetic, or memory address arithmetic, I guess the way I have this laid out, to find the memory address of any element in that block of memory. So we have the first address, and if we want to get the value at any index, say we want to get the value at index 0, this zeroes out, and it's just the first address. That's already the address of the first element. And any other index we want, we're going to multiply it by the number, the size of an element. So if we have a 64-bit value, that's going to be 8 bytes. Memory's always in bytes. That's going to be 8 bytes. So whatever the index is times 8, the size of each element, plus the first address, that's going to take us exactly to the memory address of the first byte of that value. We read 8 bytes, and that's the value at whatever index we're looking at. And the way the math works out when index is 0, since this does cancel out when we get the first address, that's a big reason why we index from 0 in computer science. It makes this equation work super great, so we can take the index and find whatever we're looking for. If we indexed at 1, then we got to do some weird off by 1. We have to do index minus 1, some weird arithmetic to get that value. With index at 0, it's nice and clean. And we can't change the size of an array. So once we ask for that chunk of space, we have to ask for a specific, every time we get heap space, by the way, we have to ask for a specific amount of heap space. So we ask for a specific amount. We say, I want an array that's going to be able to store 10 integers. We get enough space to store 10 integers. We get our 640 bytes, or 320 bytes for integers. And that's the amount of space that we get on the heap. And the space right before that or after that, specifically after in this case, is what we would need if we wanted to add an 11th element. That space might be used by another program. It might not be used at all, but we can't ever ask the operating system for a specific chunk of memory. We can't say, give me the bytes from memory address X to Y. We can't do that. That's not the way operating systems work. We can go to the operating system and say, I would like X bytes of memory, and then it's up to the operating system to decide which bytes to give us. No program can ask for specific bytes. So we can't say, can you give me those 8 bytes right after my array because I'd like to add 2 more ints to my array. Can't do it. Not allowed. Arrays cannot change size. It's not the way computers work. We cannot change the size of an array. I mean, I guess unless you write your own operating system. I don't know. Something. I said computers. I kind of regret that. It's not the way operating systems work. It's not the way we program operating systems. Technically, you could write a computer from the ground up where you can do that. Not worth it. There's a reason why things are like that. So you get your reference, which is going to be OX200 in this case is going to be the first byte of the first value in the array list. And then we're using our pointer arithmetic. So say these are ints, so these are 4 bytes. If the first value is OX200, then the next one, I knew there was something in these slides that I didn't like. I forgot to update it. It's this 12 right here. That shouldn't be a 12. So the first byte, the first value's first byte is OX200. So this 10 is stored in OX200 to OX203. That's the 4 bytes for this value. Then the next 4 bytes for this value, next 4 bytes for this value. And since these are hex values, this 212 should be 20C. 20C. Because this is a hex value. I'm treating this like it's a decimal. I just wasn't thinking when I made the slide. But this should say 20C since it's a hex value. And the way this lays out, it makes our values work here, our equation work here. For an int, the size of an int is 32 bits, so it's 4 bytes. And we multiply that by the index we're looking for. If we want the value at index 2, right here, we take OX200 plus 4 times 2, which is 8. We get OX208. That's going to give us the memory address of the first byte of this value. And then we know it's 4 bytes large, so it's 208, 209, 20A, and 20B are the memory addresses that we have to grab for the 4 bytes. Read those bytes, and that's going to give us our value that we're looking for. We call this random access. We can access any value in an array very quickly, and it gives us a lot of efficiency. It's a multiplication and an addition. That is how we figure out where the value is that we're trying to read, and it's very quick to do those 2 operations, and we go right to the value that we want to get. And this is why we call memory RAM, random access memory. This is why we call it RAM, is because your memory is a giant array. It's an array of billions of indices, and we can access any memory address. As long as we have the value for the memory address, we can go right to that memory address with no extra work. Do you explain the hex value thing real quick? It's not relevant to 116, so I'll make this very brief. But hex, instead of base 10, like all of our numbers here are base 10, where you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once you get to 9, you can't add, like there's no 10th value. So you have to add a 10th digit to get to get 10. It's 1, 0. So we have a 1 in the 10s digit and a 0 in the 1s digit. With hex, it's the same thing, but it's base 16. So you can go up to 15 before you have to roll over to 1. So 1, 0 in base 16 is a 1 in the 16th place and a 0 in the 1's place. So we need new symbols for 10 through 15, and we use A through F for those values. So A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15 in hex. It's other than that, it's the same idea as base 10. Kind of like binary is the same idea, but it's base 2. This is our base 16 variation, base 16 way of representing numbers. So this should be a C because it's 2 in the 256th place, 0 in the 16th place, and it should be a C for 12 in the 1's place. Cool. And it's a way of, when we have binary values, it's a way of us grouping 6 bits together. So one hex digit is 4 bits. So instead of writing a whole bunch of 1s and 0s, hex lets us compact that so it's easier for us humans to read. So we're not looking at just endless strings of 1s and 0s. And then two hex values is can represent 1 byte. So if you have like 2F, that would be one specific value that a byte can have. So it makes things just more convenient. Okay, and finally, let's get to the big show. Oh my goodness, it's 8:20 already. We'll be fine, but I just didn't expect that much time to go. I think I spent a lot of time introducing the homework. I usually don't introduce the homeworks in the fall and spring semesters. But they're most of what you'll be doing this semester. You won't have the interviews, and you only have 2 quizzes. I think that's worth spending some time on. So a linked list is still sequential, meaning order matters. Order matters in a linked list, but the big difference is the values are spread all across memory. So instead of having one continuous block of memory, each value in a linked list can be anywhere in memory. We don't care where these things are. We just care that we have references for each value. We have to know where each value is. And we know that by knowing the address of the first element, which I don't even have on screen here. We have the address of the first element in the linked list. We know where that one is. And then the first element and all other elements are going to have the memory address of the next element in the list. So each element knows where in memory to find the next element. And that's a linked list. That's the crux of a linked list. So we start at the first one. We can get its value and ask it where the next element is. Hop over to the next element in memory and get its value. Ask it where the next one is, and just keep hopping all across memory like this. So when we create a linked list, we don't create one big old linked list. We create each element of the linked list one at a time, which I'm going to end up calling nodes. So we create each node. We go to the operating system and say, hey, I need space in the heap for one node of my linked list. And that node is going to need space to store one value of the linked list and enough space to store a memory address for the next value of the linked list. And if we want to add to the linked list, we go to the operating system, say, hey, I need space for another one of those nodes. And then we manipulate the references to link these nodes together, which is how we get linked lists. So all these values are wherever in memory. We don't care where they are. We just ask the operating system for enough memory. We don't care where it puts that memory. We just care that it gives us the location. It gives us that roadmap, those references to find out how to find those things. And we're going to null terminate these lists. So when we get to the, how do we know when we get to the end of the list is our big question. We're going to hop node to node and ask each node where the next node is. Somehow this has to end so we don't have an infinitely long linked list. When does it end? It's when one of these links stores a reference of null for its next node. When we ask it for, hey, can you show me where the next node is in this list? It says null. Null is a special keyword, which means this variable is supposed to store a reference. It's some place where we're supposed to have a reference, not necessarily a variable, but any place where we're supposed to see a reference. Null means there is no reference. I have no reference for you. So if we ever see null, that means that there's supposed to be a reference here, but there is no reference here. Where this is going to be very important for your homework, if you ever see this error, is when we get a null pointer exception. So if we use the dot operator on a reference, that's how we say, hey, reference, take me to the object to which you refer. And it takes us over to the heap. We follow the instructions, the roadmap, and get to that object on the heap. If we try to use the dot operator on null, we're saying, hey, null, take me to the object to which you refer. And null says, dude, I'm null. Like, I don't refer to anything. And it's going to throw a null pointer exception. It's going to say, yo, I don't refer to anything. I'm nothing. Yet this dude just tried to call the operator on me and tried to ask me where my object is. I don't have an object. I'm null. And it's going to crash the entire program with a null pointer exception. So when you see null pointer exception, that means you have the dot operator on null. So checking for null, we're going to have null checks all throughout our code. Checking for null is going to be important because we will be using null to indicate the end of our linked list. So if you ever get a value that could be null, you have to check, is this null? If it's null, don't do anything with it. Don't use the dot operator on it. If it's not null, if you say if this thing is not null, then use the dot operator, that's fine. but you have to check if it's null first. That's any null pointer exception. The only thing it can be is that you didn't check for null. Somewhere in your code you did not check for null before using the dot operator. And in office hours, when I inevitably get this question a whole bunch, probably today, and the TAs will get it tomorrow too, and it'll be all over Piazza, these null pointer exception questions, it's because you have the dot operator on something that's null. So wherever you have the dot operator on a linked list node, make sure it's not null first, because you're missing a null check. A lot of times this will be in your testing. And so keep in mind that when your tests are executed, it's going to be executed against some intentionally incorrect solutions in AutoLab. So if you're not checking if everything is null in what's returned by the method, even though I know your method isn't returning null and it's passing in IntelliJ and everything's fine, and then you submit to AutoLab and it's a null pointer exception, it's because your tests are being ran against incorrect solutions in AutoLab. And in general, when you're writing tests, you should not assume anything about what you're testing, because you're testing it to make sure it's correct. If you're going to assume that it's correct, which a lot of students do in their tests, just assume that what it gives me is correct, and then I'll have one assert because Jesse says I have to have asserts or else he's going to fail me, and just have some assert for window dressing. If you're going to assume that the method is correct, why are we even writing tests? Like, we're not going to write tests for something that's just assumed correct. Like, I know it's correct. It's right. I just wrote it. It's right. I'm only writing tests because it's a 116 assignment. That defeats the whole purpose. We're writing tests because we need to actually check if the method is correct, which means your tests are going to be ran against incorrect code. If your tests are never ran against incorrect code, then you wasted your time writing the test. Not necessarily. You still gain confidence that your code's correct. But that's its purpose, is to be ran against incorrect code sometimes. So you want to make sure your tests don't crash when ran against incorrect code. And the way to do that is to always assert that any properties about what's returned. Don't assume. So we're going to assert that the value is not null. This can be as simple as assert true. The thing I'm checking is not equal to null. That's fine enough. Check that. And then if you get to the next line, that means that assert passed and it is not null. And then you can use the dot operator on it. Or use assert null and assert not null are different asserts. Just like we have assert true and assert equals, assert null and assert not null also exists. A lot of that's going to make more sense when you start the homework. So if you do see null pointer exceptions, you might want to go to that spot in the video. But I don't have enough time to keep talking about that right now. So let's get into what linked lists are. And this is it. This is pretty much it. So let's talk about this. So we're creating a class called linked list node int. This is going to create a linked list of integers. Well, actually lowercase I ints in this case. This is going to create a linked list of integers. And we do this through the node class. So each node in a linked list is going to know two values, two things. One, the value stored at that location in the list. And next is, I'm using the words value and next in my explanations. Two things, two variables, two instance variables in each node. The value stored at this value in the node and a reference to the next linked list node in the list. So for each linked list node, we know the value at this node, at this point on the list, and the directions of where to find the next value in the list. That's really it. Those are the two things that a linked list needs, is these two values. Once you have these two instance variables, you can create your linked lists as long as you have ways to set them, which we're doing through the constructor here. And to create a linked list, the way I'm doing it right here is I'm going to create a new linked list node with the value 1 and next of null. So this is how we'll create a linked list of size 1. We'll create a brand new node, give it whatever value is stored at that node, and then a reference to the next value. That reference is null for this one. So I'm creating a linked list of size 1. It has the value 1, and then its next is null, so we know there's not another value to look at. And I'm going to store that in a variable. This is what's called the head of the linked list. First is storing the head of the linked list, which is of size 1 in this case. And then this code gets a little tricky. We'll go through the memory diagram in a bit. because this one always trips students up. We have first equal to something that uses first. So what's the value of first at which point in time? Gets a little tricky. But we're going to reassign first to the value of another new linked list node. So we're creating another new object. We're going to the operating system saying, I need enough space for one int and one reference. Again, get the value 2. And then its next is going to be whatever the value of first was, which is a reference to this linked list node that was created here. So, and then reassign that to first. So first is going to equal this linked list node with the value 2, and its next is going to be this linked list node with the value 1, whose next is null, so we've reached the end of the list. Then do it again, create another linked list node of 3, and next is first, which is now this linked list node with the value 2, and then reassign that to first. So now first is equal to a linked list node somewhere in memory with value 3. It's going to have a reference to this linked list node of value 2, which is going to have a reference to this linked list node of value 1, which has a reference of null for next. So we have officially, effectively, in the variable first, a reference to a linked list with the values 3, 2, 1. And that looks like this. So first is our variable on the stack, which stores a reference to the node with the value 3. Its next is a reference to the node with the value 2. Its next is a reference to a node with the value 1. And its next is null, indicating the end of the list. So what we actually store on the stack is a reference to the first linked list node of the list. That's all we store. That's the only thing that's stored. And this is why we need to know references. I should have gave this disclaimer at the top. We need to know references from last Thursday's lecture. If you're not 100% solid on references, it's going to be really hard to learn linked lists. These lectures do lead into each other very directly. So the reference stored here in our stack, it doesn't store a linked list. Sometimes in my descriptions I'll say, create a linked list. I always mean linked list node. We're only using the linked list node class. This stores a linked list node, which is the first node in the list. But in my descriptions, when I'm in the English descriptions, when I'm not describing the code directly, I will say things like the song class needs to store a linked list of ratings. And then it's up to you to understand that means, a variable that we think of as storing a linked list is going to store a reference to the first node. So I try to distinguish. Whenever I'm talking about code, I'll say linked list node. But if I'm not talking about code, I'm just talking in English and abstracts and generalities, I'll sometimes say linked list, and you need to know linked list is a reference to the first node in that list. Because that's how you're going to hear it in your whole career. Nobody's going to say linked list node after this lecture, except within 116. Oh, and 250. In 250 they will also. And I think 220. I think they do a little bit of linked list stuff. But after that, nobody's going to talk about linked list nodes. They're just going to say linked lists, and they're going to assume that you know that it's a bunch of nodes. Oh, that was more than I thought. All right, T down. We're in it. Okay, and let's see how this works through a memory diagram. I think this gets a lot more clear when you see the memory diagram. Me talking through the code, that's fine, but it's only going to get us so far. Let's visualize what's actually happening here in memory, because there's a lot of bouncing around the heap, so let's talk about it. We're going to start with the main. We're going to create our linked list node. And just for the slide, I'm going to abbreviate this LL node. I mean linked list node when I say that. It's just so everything can fit on the slide. Like this line right here, when it's linked list node, or linked list node int, as it was on the previous slides. I just don't have enough room for the memory diagram then. It's hard to fit everything on the slide. So LL node is the same thing that we were talking about earlier. We have the constructor. This first line, easy. I mean, the new thing is null, but we've been creating objects for, 5 days. One lecture. Not all that long in the summer. Usually I'm like, we've been doing this for weeks. Or 1 week. But the constructor should feel pretty comfortable to you. You should be able to trace through a constructor call at this point. and get this as a reference to the object that's being created, the name of the object. The only new thing is null, which null, just transfer it over. Next equals null. Even if you don't understand what null is, you should be able to trace this code and just put null and be like, well, this null thing's weird, but whatever. I'm just going to write null in my memory diagram and hope it's right. You'd be able to do that. But null, this is the way it's represented. We're just going to write the word null. That gets returned to first. And now one of the tricky parts, we want to make sure we're tracking what's happening with the variable first. So when we execute this line of code, we always execute the right-hand side of the assignment first. We have to resolve this to the value that we're going to store in the variable. So on the right-hand side, we need to resolve the arguments before we call the method and create the stack frame. So 2 obviously just resolves to 2. But first, we have to resolve this. And at this point in time, first is OX350, a reference to this node right here. So first resolves to OX350. That's what next gets. And then we're going to create the new object. We get to call the constructor after resolving the arguments. We call the constructor, create this object. It gets whatever reference you want. If you're doing the tracing tool, this is OX02, OX03. We get this node. I'm just making up random numbers since I'm doing this on slides, not on the tool. And this is going to be a reference to the object that's being created. And next is what first resolved to from the main stack frame. So this is what we get, and then we assign value and next over to the instance variables and return a reference to the object that was created. So this node's next is going to be that initial node that was created, and then we return OX200, and now first is going to get the reference OX200. So first is now a reference to OX200, which is this node right here, which its next is the value OX350. So we can still access this node. If you're really paying attention to the last lecture, this looks very similar to the first 2 lines we did before where we got garbage collected, where this node gets garbage collected. That does not happen here because we can still access that node. We don't have a reference to it on the stack anymore, but we can go through it by composition here. We go first dot next dot and still access this variable. Indirectly through this reference, we can still access this object, so it does not get garbage collected. It's not the same situation because we can access it. And then we do it again. We put the third constructor call on the stack. First, at that point in time when this was being resolved, first was OX200. So next got OX200. We create a new object. This gets its own memory address. And these memory addresses are anywhere in memory. I purposely did the memory addresses out of order to emphasize that it's wherever the operating system decided to give us space. We don't know. We don't care where that is. We just know that somewhere in memory, the operating system gave us enough room for what we asked for each one of these nodes. And it gave us some reference, which is the location in memory where it decided to give us some space. It can be anywhere. It can bounce all around like this, and that's fine. And that's the advantage of a linked list, is that whenever we add a value to a linked list, we ask for more heap space. And no matter where that space is, we link it to our list through these references of next. So next was OX200. When we made that call, we got OX480 was the random number I came up with for this one. So this is OX480, a reference to the object being created. And then it returns 480 back to the stack, back to first. So at this point in time, first stores a reference to OX480. That's the head of our linked list. OX480 has the value 3 and next of 200. Which has the value 2 and next of 350, which has the value 1 and next of null, indicating that it's the end of the list. So the way we think of this as humans is we would say first stores a linked list with the values 3, 2, 1. But in the computer, the way this is represented, and the way we have to think of this as computer scientists, yes, I'm implying computer scientists aren't human, we think a little different, is that this is a reference to the first node in the linked list. which has the value 3 and a reference to the next value, which has the value 2 and a reference to the next value, which has the value 1 and a reference of null for the next value, saying it's the end of the list. I mean, we are humans, but we definitely think different. Okay. Then first only stores the head of the linked list. Of course, now with AI, there are developers that are not human, literally not human anymore. And I made those points when I was talking. And let's see our first algorithm on linked list. Actually, let me pause a little bit because that's a lot that we just saw. So we'll wait out the stream delay for any questions here. Because that's everything I have to say about the structure of a linked list. This is how linked lists work. If you fully understand this, the rest of this lecture is not really going to be anything new for you. There will, but there won't. Because if you understand this, you could figure out all the rest of the stuff that we're going to talk about. So this is the crux of it. The idea that a linked list is a series of nodes where each node has a value and a reference to the next node. We only store the head of the linked list, the first node, in our variables that we think of as storing linked lists, and the last node has a reference null indicating the end of the list. That's it. That's the structure of a linked list. That's all I have to say about it. The rest of the lecture is algorithms, like how great that's the structure of a linked list. How do we work with this? How do we actually use this to do something useful? That's algorithms, which will be most of the rest of things. And then we're going to talk about stack and queue at the end to show two examples of applications of linked lists that are pretty common out there. We've been talking about the memory stack. It's even on screen right now. The memory stack all semester that follows the stack structure. We're going to talk about how to build a stack, not a program stack like this, but a generic stack using a linked list. Okay, I think I rambled enough for the stream delay, and there are no questions, so pushing on. If y'all don't slow me down, I'm going to keep going. All right. So, and I kind of do have to keep up this pace because this is how we hit our timings. So let's see our first algorithm for a linked list. How do we work with a linked list? And my first question is just how do we visit every single node? All I want to do is visit every single node. And in this case, I'm going to write a toString method. So when I print a linked list to the screen, even though I'm just printing the head node, I want that to go through all the nodes and print out what I would expect when I print out a list. I want to get all the values of that list. So let's give it a toString method. And this is going to go through the whole list and concatenate all of the values of the list together and then return the big concatenated result. And it's going to use recursion. So I promised recursion would come back in a big way. It's coming back today, and it'll come back even bigger next Tuesday. Oh my goodness, this summer goes so fast. Even I'm surprised. It catches me off guard, too. Is that true? I don't know if I even believe that. Linked list. Yeah, trees. Tuesday, June 18th. Wow. That's fast. Y'all got to keep up the pace. This is a 6-week sprint. It's a definite endurance test. Testing your sprinting endurance, nonetheless. That's tough. So recursion's coming back. It's going to come back a lot bigger next Tuesday. I'll give my disclaimer right here about recursion. You can do all the linked list stuff. You can do task 3 without recursion. I do not recommend that. I recommend using recursion to get practice with recursion right now while the recursion is still pretty simple, because next week when we do trees for task 5, the recursion, you're not going to, how do I word this? You're going to want to use recursion. you're going to want to use recursion. A lot of students for linked lists, they're like, I ain't using recursion, screw that. But when you get to trees, you pretty much have to use recursion. If you don't use recursion, then you're creating way, way, way more work than is necessary to get the job done. So you're going to want to use recursion when you get to trees. And if trees are the first recursive methods that you're writing is on task 5, that's going to be a very, very tough method to write, because you have no idea how recursion even works to begin with, how to write a recursive method, and you're trying to write a doubly recursive method on a tree. That's going to be tough. So I recommend getting your practice with linked lists while the recursion is more straightforward. Are trees the last topic that could be on the midterm? Yes. Yes. I had to double check that because I was contemplating not putting trees on the midterm. I guess I still have the option of not putting trees on the midterm. Like, well, we kind of need trees on the midterm. We really need trees on the midterm. That's why I put it like that. I just duplicated my thought process. Yeah, we need trees on the midterm. But yeah, trees are the last topic that can be on the midterm. So we're using recursion. So, and here's your big memory diagram for the whole thing. So I added the toString here, and I changed the code a little bit, but added the toString. Just to make that toString explicit. This is implicit that we're calling. Oh no, never mind. I didn't even change anything. I just changed the variable name. But here's what the whole thing looks like with the toString and creating the linked lists and everything. Again, the big difference is that the main stack frame is explicit. Other than that, really no real difference between the tool and the slides, except the way that it looks, the way the information is presented. But let's go through this. And again, when I do the live coding in the 11 a.m. lecture, I also do the tracing tool for the memory diagrams. I don't use these slides like this. So if you do ever want to see, if you're studying, watching lecture and it didn't, or just watch the other lecture if it fits in your schedule. So just a reminder on that. Okay, so we hit toString. All the rest is the same, creating the linked list, and then we hit toString. First dot toString. So we call the toString method through first. So first dot toString. We call toString from this object right here. We look in the LL node class for a toString method, and we find it right here. And the calling object was OX480. So this is OX480, a reference to the calling object. We call the method, we set out to the empty string, and then we immediately cross that out and replace it with value. I wish we did this on one line, but whatever, it's 2 lines. So out plus equals this dot value. So out plus equals this dot value. Dot always means follow the reference to the heap, to its object on the heap. So it's 3. And the reason we have out equals empty string and then adding, that's so this plus is going to be a concatenation operator. If we said string out equals this dot value, we get a type mismatch. Usually Java is pretty good about converting things to strings like that. In this case, it would not be. It would say expected a string, but you gave me an int. What the hell? What the hell is going on here? So we do it in 2 lines. Now this is the concatenation operator, which is really good about converting ints to strings. So that's the reason why we have this line that seems like it's doing nothing. And then our first null check. Whenever we're working with a linked list, we're going to need our null checks. They're going to be everywhere. Everywhere we're going to have some null checks. So if this dot next not equal to null. So if this dot next not equal to null. So what we're saying is if we're not at the end of the list, then do this code. And here we have this dot next dot toString, our recursive call. Once we say next dot, we're risking a null pointer exception right here. When we hit this dot operator, if this dot next is null, that's going to give us a null pointer exception. So we had our null check. If this dot next not equal to null, we're saying if it's not null, then we're going to use the dot operator on it. You're going to see this all throughout linked lists. Hopefully, anyway, if you don't have this in your code all throughout your linked list, then you're going to have null pointer exception errors in Autolab. So hopefully you have this all throughout your code when you code task 3, is these null checks. We're going to check for null, and if next is not null, then we can safely use the dot operator. Never just rush in and use the dot operator on something that you haven't checked whether or not it's null. If you haven't checked whether or not it's null, it might be null. Sometimes it might be null, and sometimes you'll get a null pointer exception. So we checked, made sure it's not null, and then called the dot operator. This is our recursive call. So this dot next dot toString. We're calling toString from this node right here. We call toString from this node right here. We look in the LL node class for toString, and the calling object is OX200. So we get a stack frame where this is OX200, and then we go through the method again. Out equals empty string, out equals this dot value. So we get out of it equals 2, and then checked for null. If next is not null, this dot next is not null. So we're going to execute the code in the code block, which calls this dot next dot toString, this dot next dot toString. From this object, we're calling toString. So we get another toString where this is OX350. And this one, we're going to check this dot next not equal to null is false because it is null. So we skip this code block and just return our out, which is the string 1. So we return 1 to the previous stack frame. And again, in the tracing tool, we don't have a mechanism to write an arrow that points to another stack frame. In this case, you could write your arrows pointing to out. It is plus equals. It's not a strict assignment, but I wouldn't be mad at that. But if you don't have these arrows, or if you point to out, or if you point to value, I'm not gonna sweat that. However you have your return arrows, or if you don't have your return arrows for your recursive calls, I'm gonna be okay with that. If it is a strict equal, if it's out equals the recursive call, then it should point to the variable, but again, I'm not going to sweat it. So this returns 1 to the previous stack frame, which was waiting right here for this recursive call to end. And this recursive call resolved to the string 1, so it's going to replace out with the empty, or set out equal to out plus the empty string plus whatever the return value was, which was the string 1. So out was 2, so it's 2 and then a space and then the value 1. And then that's what we're going to return from this stack frame. This stack frame returns 2 space 1 to the previous stack frame. So this resolves to 2 space 1 in this stack frame, which is now the top of the stack again. Its out was the value 3 plus empty string, or not empty string, plus space, and then whatever the recursive call resolved to, which was 2 space 1. So 3 space 2 space 1 is our final result. That's what we're going to return to the main stack frame. So value gets 3 space 2 space 1, and then that's what we print to the screen. Oh my goodness, we went over in the first lecture. It's the second lecture that takes the longest out of these 3. So if there are questions, I'll keep an eye on chat. If there are questions, to circle back around to that. But let's keep moving. Why do I have 2 of these open? And so this is shifting into Wednesday's lectures, the next set of slides. Well, you saw me switch the slides, so I guess that's obvious. In the next lecture, it's not as obvious, so I've been remembering to mention it each time. So now let's go kind of rapid fire through some linked list algorithms. toString was your first taste of it. We saw a reminder of recursion, how we're going to use recursion to go through linked lists. So we're going to see that 4 more times. I think there's 4 examples in this lecture. And And before we get into that, we got to fix something here. We created this linked list node int, and if you're paying attention last week, if you're really paying attention, I said when we get to linked list on Tuesdays, I'm going to show you about this angle bracket, this type parameter, all that crap that we've been talking about with array list and hash map. We're going to do that with our own data structures. And then I show you an example that's linked list node int, that's hard-coded to an int. Let's fix this and get our linked list to work with any object type or any class type. So how do we do that? Instead of creating linked list node string, linked list node double, linked list node boolean, we don't want to do that. Linked list node player, linked list node rating. We don't want to create a new class for every single type that we can store. So what we're going to do is the same thing that we do with array list. Allow the user to specify the type and create a linked list node of any type that they want, as long as that type is a class type. So they're not going to be able to create a linked list node of a primitive type. That's still not going to be allowed because Java doesn't let us do that. But we're going to let them use any class type. And we're going to do that like this. So we're going to replace that type. Wherever we had int, we're going to replace it with a placeholder type, which is actually a variable. This is a variable name. So in the class definition itself, linked list node, we're going to specify a type parameter list, or as Java calls them, generics. So if you ever hear people call these generics, I'm going to call them type parameters because that's just what I know the concept as. In the world of Java specifically, they are called generics. So they're called something different in each language. I think C++ calls them templates, if I'm remembering right. I think of them as type parameters. I think that's the most descriptive name for them because it's a parameter list that takes types. What else would we call it? Why do we call it generics? Generics at least makes sense because it's a generic type. It could be any actual type, but we just code it to a generic type. So we specify our type parameter list right here. I'm going to name my type capital T. This is the naming convention. Like, this is a variable name. You can name this whatever you want. The naming convention is one single capital letter for your type parameters. So if you're reading somebody else's code and you see some variable name that's one capital letter, you know that that's a type parameter. Or it's your friend trying to screw with you so you can't read their code. It should be a type parameter if you see a single capital letter. So with that naming convention, it just makes it a lot easier for us all to read each other's code. Lowers the tax on our mental capacity. So that's our type parameter list, and then wherever we use that type parameter, we're going to put T instead of any other type. And then when we use this code, we're going to create not just a linked list node or a linked list node int, we're going to create a linked list node of integers, how we read this, so that we're specifying the type parameter as integer, and then for this specific linked list node object, the constructor will look at where it's being assigned, and it'll look at this. In this case, it'll look at the parameter, the argument type, and see that it's an int and figure it out. It has a few ways of figuring out that it's a linked list node of integer. So the type parameter is going to be integer in this case, and these t's are effectively replaced with integer for this linked list node object. It is not literally replaced. Never go through your code and replace t with rating. I'll see that each semester. Don't change that. This is a variable name. So if you change t to rating, you haven't changed anything at all, and it certainly doesn't do what you want it to do. You put rating here. You create a linked list node of rating. Here's where you want to put it in your type parameter when you use the linked list node. You don't need to change the linked list node class that was provided at all to complete task 3. You don't need to change it at all. I think I put that in the homework document because people kept changing it. They would change this to ratings, or they'd hard code this to ratings, and it's just not what we're doing. We use type parameters. So now we can create a linked list node of integers. If we, I got ahead of my slides. And then our linked list node should refer to another linked list node of the same type. So we code these to be the same type as each linked list node that refers to it. So our whole linked list is going to be the same type. I mentioned all this. And then if we want to create a linked list node of strings, we change the type parameter string. Our code hasn't, for the linked list node, hasn't changed at all. It's still t, because t is a variable. But in this case, if I create a linked list node of strings and put strings in it, this is all valid code. All these t's are effectively string for this particular linked list node object. They don't actually change, because I can have a program where I have a linked list node of strings and a linked list node of ints, just like you can have an array list of strings, an array list of ints, an array list of players. You can have all those in the same program, because the array list just has some type parameter that can be different for each object of that type. So now our linked list can store any type. Our linked list is, I shouldn't say as powerful, but it's as flexible in terms of the types that it stores as an array list. You can store any type that hasn't even been created yet. If you write a brand new class or a brand new type, this linked list can store that type. Okay, so now we have a generic linked list, and linked list looks a lot more like the handout in the project. So now, let's get into some algorithm. Actually, we have one more background. So let's write our getters and setters. So I got away without getters and setters in the previous example, in the previous slides, because the code that I wrote that used the linked list, the main method that used the linked list, was in the linked list node class. That's rarely going to be the case. I just did that to keep the first example a little bit simpler. So I could do .value and .next. That's not how we're going to use a linked list. You're never going to do .value and .next. You're going to use getters and setters and private instance variables like we do in Java. So I'm going to write our getters and setters. A getter for value, a setter for next, and a getter for next. And I'm not going to have a set value. For what it's worth, I don't want anybody changing the values of my linked list nodes. If you want a setter for value, that's fine. You can write one. For task 3, there's not going to be any need to set the value after it's set. If you want to change the value, you could always create a new linked list node and replace some references to change the linked list that way. So this should help with making multiple linked lists of different types. Yeah, so you're able to create multiple linked lists of different types with this class the way it's written right now. For test 3, you only need one linked list, and it's of type rating. But this gives you the flexibility. Maybe that's where the confusion comes from. Maybe I should make you write 2 linked lists of different types. I don't know. I don't think there's much confusion. It's only like 1 or 2 students each semester. And that's when it's hundreds of students. We have 94 in the summer. It's possible that none of you even make that mistake this semester. Of course, it's 1 or 2 out of the ones that those are the ones that I see. So it's probably more like 10 or 20. That the TAs handle, and I never get to know. So there's our getters and setters, so we're doing things properly. And finally, here are the 4 algorithms that we want to implement today: size, append, find, and min, which do pretty much what you would expect them to do, with the exception of min. Well, it does what you expect it to do, but how we do it is going to be a little bit different. Size, append, size does what you expect it to do. How many elements are in this linked list? Append does hopefully what you expect it to do. It's going to add an element to the end of the list. Very important that this is the end of the list. So the only example we saw already was using what's called prepend, where we're adding elements to the beginning of the list. So we added 1, 2, 3, but the list came out 3, 2, 1, because each time we added, we were adding to the beginning. We're prepending to the beginning of the list. We want a method that's going to append to the end of the list, which is more how we use our data structures. When we call add on an array list, it's going to add to the end of the list. So let's write a method that does that. Find, which is given a specific value, return the first node you find that contains that value. And then min, we're going to create specifically a linked list of doubles and return the minimum value in that list. This last one is going to be the most important. The first three are going to warm up to the last one. And the last one, this min, is what's going to parallel the homework pretty closely. And I'll explain when we get there, but the first three and the toString that we saw are going to use a different setup than the last one. The last one's going to switch it up and parallel the homework a bit more. So make sure you're understanding these first three going into min, or else you have no chance of understanding min. And then min is the one you want to be hyper-focused on if your goal is to complete the assignments, which I hope it is. Some students, I wonder, some students still haven't finished task 1. I don't think their goal is to finish the assignments. Some, you know what, you want a quick timeout for stats? 3, 4, 5, 6. There's 94 students in the class right now. 6 of them have not... I'm on task 1. 6 of them have not made a single submission for task 1. Those 6 students, their goal is not to complete the task. Their goal is to fail this class as fast as possible. And they're going to accomplish that. They're going to do a good job. So they created a goal for themselves. They set out to accomplish it, and they're going to accomplish that. They're going to fail as soon as they hit the expected deadline of task 1, because they're not responding to my emails, and they haven't even done anything with the course yet. Very, very good way to fail. Very effective. So let's start with size. Let's go through these 4 methods, which suck. Like, there's nothing I can do for them. Like, I don't know. I'll send them another email when we get closer to the final deadline for task 1 saying, dude, you're about to fail. Like, right now. Maybe some of them will respond to that, but I'll try, but I don't have too high hopes for them. All right, so with size, what we want to do is navigate through the entire list and count 1 for each node that we see as we go through the list. And we're going to use recursion here. So with size, I want to call size. I'm going to call size on the head node, so on the very first node of the list. And I'm going to check if next is null. So if next is null, what I know is that I'm looking at the end of the list. This is the last node of the list. If next is null, what I have is a list of size 1. And here's where the recursion's going to start getting a little trickier to wrap our heads around. And I think this is why I've challenged some students when they use loops for all their linked list stuff instead of recursion. I'm like, you're not getting the practice? And they're like, I just couldn't wrap my head around that, man. I'm trying to get through task 3. You only gave me 2 days to do this. Like, I just had to get it done one way or another, which I understand, you know. So I'm going to try to explain this in a way that hopefully makes sense. And if it doesn't, we'll catch up on trees. We'll get you using recursion on trees. But one of the big things, and I would like my visual on screen while I do this. So if I call size on this node right here, since what we store in memory is a reference to the head of the linked list, if I have a variable that stores a reference to this node right here, then this node is effectively the head of that linked list. I effectively have a reference to a linked list of size 1 that has just the value 1. Likewise, if I have a variable that stores a reference to this node here, then I have a reference to what I would think of as a linked list of size 2 with the values 3 and 1. So I effectively have 4 linked lists on screen right now. We like to think of it as just one linked list because we'll usually have a reference to this node here. If we've created these 3 nodes, we probably want all 3 nodes. So we'll have a reference to this and have the full 4, 3, 1. But I could have a reference to this node or a reference to this node, or I could have the reference null and have an empty linked list. Null is going to be how we'll represent an empty linked list. So I can have a reference to this node, this node, this node, or null for a linked list of size 0, 1, 2, or 3. And size doesn't really work for size 0 in this setup, the way we have things set up right now. So we can't really get that with this method. But we have three linked lists that we could call size on and 4 linked lists total on screen right now. So if I called size on this node right here, notice that this node has no knowledge at all of the nodes that come before it. In 250, you'll talk about doubly linked lists, where nodes do have references to next and previous. We're not going to do that in 116 though. But if I have a reference to this node and I ask it its size, it doesn't know anything about these other two nodes. It's going to say, well, next is null, so my size is 1. And that's exactly what this check does right here. If your next is null, that means you are the last node of the linked list, or a linked list of size 1, rather, the way I'm framing it. You're a linked list of size 1, so you return 1. If your next is not null, what you're going to do is ask your next node, which is not null. We did our null check, so we can safely use the dot operator on next. We're going to ask it for its size. It's going to return something. It's going to say its size, and when we write recursive methods, what we can do is use recursive calls, and this part always sounds really weird when you first hear it, but we're just going to assume the recursive call is correct. We're going to assume that it works. So we're going to assume this .next.size does return its size of next, and then when we get that size, we're going to bump it up by 1 and then return that 1 to account for this node itself, and then return that value. So if I call size on this node, it's going to make the recursive call and just assume that this node returns the right value. If it returns 2, this node's going to add 1 plus that 2, 1 to account for itself, 2 to account for everything that comes after it, and then return 3. That's what we expect this part of it to do. So when you're writing a recursive method, you want what's called your base case. This is some situation where we don't make a recursive call. For linked lists, this is almost always going to be when you've reached the end of the list. So you check for null. If next is null, we're at the end of the list. That's our base case. Else, we make some recursive call. Assume the recursive call will return the right value, and then process it beyond that. Whatever this returns, whatever additional processing we need to do to make this correct, including this node, then that's what we return. So hopefully that made some sense. Recursion takes a while to fully grasp to the point where you can write recursive methods with confidence. But let's see this in the diagram. So I'm going to do what I call abbreviated memory diagrams starting in this lecture, and actually I think only in this lecture, to be honest. Abbreviated memory diagrams where I'm not going to show the whole memory diagram, but I'm going to give these kind of graphic examples just because we don't have time to go through 4 memory diagrams. So the caller, so from a main method you could picture this, or from the song class, wherever it's being called from, that has a reference to the head of the linked list, is going to ask .size, how big are you? This node doesn't know. It's going to make the recursive check, or it's going to make the base case check, which is false, so it's going to get in the recursive case. So it's going to say, hold on, I can't return quite yet. I got to put more frames on the stack and do a whole bunch of extra work before I get back to you. So it's going to put another frame on the stack. It's going to ask its next node what its size is. This node also doesn't know its size. It just knows that its next is not null. That's the only thing this node knows, is that its next is not null. So it's going to ask its next, which is not null. It's going to ask it its size. This node finally, with three recursive frames on the stack, 3 frames of type size on the stack, this node is going to say, whoa, I'm the end of the list. Or rather, it's going to think, I'm a list of size 1. So it knows its next is null, so it's going to return 1. I am a list of size 1. I don't care what you're going to do with that information, but I'm a list of size 1 if I'm the head of the list. This node gets that return value, bumps it up by 1, and says, okay, I'm 2. So this node says, okay, if the size of my next node, assuming it's the head of a list, is 2, then I must be a list of size 3. So it's going to return its answer of 3. The original caller gets its answer of 3 after all these recursive calls resolve, and it does whatever it's going to do with that information. Okay, let's move on to append. Append is a little interesting, and this kind of highlights one of the potential downsides of linked lists, if we can call it that. So the big upside is that it's variable size. We can manipulate the size of a linked list, and we can add nodes. Like if we want to add a node in the middle of a linked list, we can do that. That's perfectly fine. We create a new node, and we manipulate a few references. We change these values for next for a couple of nodes, and very efficiently we can add to the middle of the list. We can prepend to the beginning of the list. We can append to the end. But the downside is, how do we get to the end of the list? So if we're already at the end of the list, appending is easy. We create a new linked list node. The end of the list next is null. We replace that null with a new node with the value that we're adding and a next of null because that's the new end of the linked list. But we have to get to the end of the list first. So to get to the end of the linked list, it's not like our random access arrays where we can just jump to the end of the list. We can't do that because we don't know where the end of the list is. The only way to find the end of a linked list is to go through the entire linked list. We have the head of the list, we have to do .next, 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 because each node only knows where the next node is, and each node can be anywhere in memory. So we actually have to go hop around all over memory asking each node where the next node is in order to find the end of the list. So if we have a linked list with 1,000,000 nodes, we have to hop around memory 1,000,000 times to find the end of that list. So we no longer have our random access, just a multiplication and in addition, we have to go hopping all over the place to get to the end. So this can be very inefficient if we're not careful. So append is pretty inefficient with a linked list. All right, so let's append. What we're going to do is if we're at the end of the list, that's where we append. Easy enough. If we're not at the end of the list, we're going to make a recursive call to append. And we let recursion do all the actual work. The recursion is going to do all the jumping around memory for us. So if this is our linked list and we need to add 1, we're going to call that on the head of the linked list. We're going to say add 1. This node's going to say, well, I'm not the end of the list, so I can't really do that. So all I'm going to do is tell my next node to append the value. This dot next. This dot from the stack. We'll picture this is the stack. This dot next dot append. So from this stack frame, we're calling append. We're making that recursive call of append. So in the next stack frame, this is a reference to this node here. And it's going to say, well, I am the end of the list. This dot next equals null. I have nothing after me, and I was asked to add this value. So I'm going to create a new linked list node with the value that we're adding and its next of null and set my next. So this dot next equals this new node that we're creating. So where next was null, now it's going to be a reference to the new node that we just created, and that node's next is null, indicating that it is now the end of the list. So we've effectively appended 1 to the end of this list, but we had to traverse the list to get to the end before we could append. And notice that this returns void. It's called for a side effect, so the caller just has to assume that it worked in this case. This is where we'd write unit tests, test the thing, make sure the method works great, and then we just use it with faith for its side effects. Okay, and find. Okay, we're cruising now. Find, which is good because I want to spend a lot of time on the min example. Find. This one's a little bit different, but not too different. And there's one sneaky thing I have in here that I'll explain more when we get to the min method. This dot equals for foreshadow. The fact that I get away with this is strange, I guess. Not strange, but I'll explain. So the find method, we want to return the first instance. We want to ask to find a specific value and return a reference to the first node that contains that value. So if there are multiple nodes that have this value, we're just going to return the first one that we see, which is usually how find methods work in programming. They'll return a reference to the, they'll return the first node that it sees. And And we want to return the whole node. This is usually how linked lists work, because a lot of times we want to work with that node because we're going to be manipulating references. We want to find a value because we want to add a new node right after the first node that contains that value. That's usually what we want to do. We're not going to do that in 116, but just to show you that setup, we're going to return a reference to the node itself. We're not going to return true or false. That might be what you would expect for this. That would be a contains method. We're going to do find, which will return the node itself. So we're going to check this dot value, and I purposely reuse the value here just to make sure we're keeping our variable straight. But this dot value equals value. Does this node's value equal the value that I'm looking for? If it does, we're going to return this node, a reference to this node that contains the value, and return that up the recursion. Else if this .next is null, we've reached the end of the list, and we're going to return null just to indicate that, hey, we didn't find the value, it's not in this list. And then if neither of those are true, we're going to make the recursive call. So next isn't null, so we can safely use the dot operator on it. And we're going to ask the next node to find the value. And we're going to keep going down the list until we either find the value or we reach the end of the list. And the order is very important with find here. We have to check if the value of this node equals the value we're looking for before our null check to see if we've reached the end of the list. With the specific way we're setting this up, if you want to set it up a different way, you might do the null check first. But if you're setting it up this way, what we want to make sure we avoid, or what we want to make sure we do, I should say, is check the value of the last node. So if we have these flipped, we're checking for null and returning null right away. We're never checking if the last node's value equals the value we're looking for. So if the value isn't exactly the last node, we would return null and say the value's not here. So we want to check the node's value first and then check for null. So we're checking the value of the last node when next is null. In general, it's very important to think of your edge case. That's one of your edge cases, by the way. Your edge cases for linked lists are when the last node is important and when the first node is important. So specifically, your bulk of your difficulty in your task 3 is removing a rating by reviewer ID. What happens when the rating you're removing is the last rating of the linked list, and what happens when it's the first rating of the linked list? Those are two very important edge cases. You have to test for those. You have to make sure you cover those cases. And if we have these switched, we would not be finding the value if the value is in exactly the last node of the list, which would be, of course, broken code. Okay, so let's assume we have this linked list here, the one we've been working with, and we're looking for the value 3. We ask the head node. We always start our algorithms at the head node. We ask the head node, hey, I'm looking for the value 3. This node's going to say, okay, I don't have 3. My value is not 3. So this dot value dot equals 3 or value, which is 4 dot equals 3 is false. So we're going to skip to this dot next equal null, which is false. So we do have another node. So we're going to move over to that node, make the recursive call, and say, hey, next node, do you have the value 3? It's going to check and say, yeah, I got 3. And it's going to return this, which in this stack frame, this is a reference to this node. So I'm going to return myself. This node returns itself effectively. Would just return this. So it returns a reference to itself. This stack frame is going to get that reference. It made the recursive call here. This resolved to a reference to that node here. And it's going to return that reference and say, hey, here's a reference to the first node that contains the value 3. Okay, now the caller is looking for the value 8, which of course is not in the list. So how does this one work? Same thing to start. 4 is not 8, so make the recursive call. 3 is not 8, so make the recursive call. 1 is not 8, so we're importantly checking, does 1 equal 8? If it doesn't, now check to see if we're making a recursive call. This dot next does equal null, so we're just returning null and saying no, the value is not in the list here. If we have this null check first, say we're looking for 1 and we check for null first, we say, well, my next is null, so return null. And we never checked if 1 equals 1, where we should have returned a reference to this node. So always do this check first, or however you're set up, however your method is set up. In general, make sure you're not missing the last node. So return null, return null, return null. Didn't find what we're looking for. Okay, now how are we doing on time? Pretty good. We have 15 minutes to talk about min. We're doing good. So I slipped one by here. We'd use dot equals. This is a little, I don't want to say tricky, but it was deceiving, I'll say, that I snuck this dot equals in here. And we're going to see next, I almost said next week, but in 2 days, we're going to talk about inheritance, and we're going to see what this dot equals method really is, where it comes from, how it works and stuff. We use dot equals on strings and array lists. Did we use it with array lists? No. We use the cert equals on doubles is what I'm thinking of. But we saw this on strings anyway. We use dot equals to check the equality for 2 strings. Dot equals, this equals method is actually a special method that absolutely every object in Java has. Every single object has a few specific methods. ToString, you can print anything to the screen, and what the print line method does is calls ToString on that value, whatever value you gave it, and it has overloaded methods for all the primitives, so it can handle those as well in its own unique ways. Equals is a method that everything has, and hash code, something that we don't find useful in 116, but does exist. So a handful of methods that absolutely every object has. And that's how we got away with calling equals, even though we don't even know the type that we're working with. This dot value is of type T. What methods does type T have? I don't know. Is it an integer? Is it a double? Is it a player? Is it a basketball? What type is it? Is it an array list of integers? Is it a string? I don't know what type it is. I have no idea. It could be any type in Java ever. As long as it's a class type, it can't be a primitive. So as long as it's a class type, it's valid. And every single object, which objects have to be created from classes, so every single object is a class type. Every single object has an equals method. So I actually get away with this. So I get away with using equals, even though I don't even know the type of this dot value. I can call equals on it because I know it's an object, and every object has equals. I could also call toString. We took advantage of that with our toString method. We called toString on the value itself. Wait, did we? No, toString was with linked list node of int. Linked list node int class, so we didn't have to. But we could do a toString as well in the same way because everything has toString. So we can call those methods with T, but we're really limited. There's not much else we can use, no other methods, not many other methods that we can call on every single object in Java. So this isn't going to get us very far. It got us through find, and it only gets us through find if we want to use the default equals method. Like if we want to write a find method that works with strings that ignores case. So if somebody capitalizes a word and sometimes doesn't capitalize it, we want to treat those as equal. We can't even do that. We can't use this setup to do that. It won't work for us. We can only use the default built-in equals method for each class. And for strings, that's character for character. Every character is equivalent throughout the strings, and the strings are the same length. So we're going to have to do something else. Specifically when we're coding min, we're going to want to use the less than operator. And the less than operator is not one of those methods that exists in every single object ever. It just doesn't exist. So how are we going to do this? We want a linked list of doubles and find the minimum value of the double, but we can't use less than. How the hell would we do that? And if we have ratings and we want to find the average of a list of ratings where we have to access an instance variable of each value, a specific instance variable of each value, like how do we do that? Because rating dot get rating, that get rating method isn't going to exist to get the rating of each one to be able to compute the average. And if you're removing a rating by reviewer ID, dot get reviewer ID is not going to exist in every single object in Java. It's not one of the very special methods that exist everywhere. It'd be silly if it did, get reviewer ID. So how are we going to do this? Less than operator, get reviewer ID, get rating. How are we going to call these methods in the same way? And the answer is we're not. We're just not going to be able to do this setup. So what we've done so far is put all these algorithms, all these methods inside the linked list node class where we only have access to generics. And we're going to switch that up a bit and get outside of that linked list node class and show something more like what we're going to do on the homework. So here I'm going to create a new class, linked list of doubles, which is going to use a linked list. It's going to use the linked list node class to store a linked list as an instance variable, which is what the song class does. Read this as public class song, private linked list node of ratings. And this example is going to follow pretty well one for one with what you want to do. Of course, you're not doing min, you're doing average while ignoring the invalid ratings, and you're doing remove rating by reviewer ID. So you're doing different things in the end, but the initial setup should be identical. I shouldn't say identical, but pretty much the same. Like add double is your add rating method. Pretty much one for one. Like I'm always shocked when somebody doesn't have the add rating method, because I say that every semester. Like, this is your add rating method. Like, the only difference is it doesn't take a double, it takes a rating. But some people have broken add rating methods. I'm like, I know you didn't pay attention in lecture. Like, you might as well just come to office hours and say, I don't watch lecture. Fix my code for me, even though you already told me exactly how to do it. And to be fair, 2.5 hours of lecture, you're going to miss a point or two in there. Like, you're going to miss a few things that I emphasize. So I still help those students and everything. But, like, it's always weird when I can just flat out give the answers away and I still get the questions. It humors me. I get it. It's a lot of hours of me rambling to absorb every little thing I say, but at the same time, like, what else am I supposed to do when I just give you the answer and it still doesn't get through? Like, what do I do at that point? Give you the answer 20 different times to make sure you don't miss it? And I do that. Like, I'll do that sometimes. Anyway, so let's do this. So think of song and linked list of ratings, linked list node of ratings. Why does it say append of D and not add double of D? Because we're using the built-in append method. The append method that we built previously, we're going to call that method and let that method do all the work. Same thing with add rating. It'll be add rating and append right here. This will be append. Because I already gave you the append method. There's no reason for you to rewrite the append method. It already exists. Like, it's already there. I forget if I put it in the handout itself. I'll have to check that. Because I used to, and then I didn't, and then I think I did again. I don't know. I don't remember where I'm at right now. But if it's not in the linked list node class that's given in the handout, you can copy and paste it from the lecture example and put it right in there. It should be in there because I say you can cut and paste it. But the append method already exists. What you have to do is check if... Actually, this is part of my explanation. I'll get to it all. But you can call that append method. It already exists. Like, don't recreate it. There's no reason to recreate it. Just call my append method. It already does exactly what you want it to do. Okay, So we have a linked list node of doubles as an instance variable of this class. This is what we want to do, and now whenever we work with this linked list node of doubles, which I call numbers here, whenever we work with numbers, we know that it's a linked list of doubles, and we can do all of our doubles stuff, including the less than operator here, because we know that we have a linked list of doubles. We're not in the linked list node class where we have to assume that this could be any type ever. It's a value of type T. Now that we're outside of the linked list node class and we have a specific object of type linked list node, that object has a specific type parameter, and now we're working with that type parameter. That linked list node of double, we know node's value is a double, so we can work with this node. We can work with these values as though they're doubles, as though they're ratings. We can call the specific methods on these types because we know the types. Okay. And when we're creating a list like this, so in the linked list node class, we had no way of representing an empty linked list. But now that we're outside the linked list node class and we have a variable, this numbers variable stores the head of a linked list. If there is no head of the linked list, if the list is empty, we're going to set numbers equal to null. So if our variable itself is equal to null, that's how we're representing an empty linked list. Do not, and I'll see this, I already saw it this semester, students getting ahead but not watching the lectures ahead. Figure that one out. Do not create a new linked list node of null. Never create a new linked list node where the value is null. That should never happen in 116. There are cases out there in the wild where that'll be what's called for. In 116, that will never be the situation. This first argument of the linked list node constructor should never, ever be null. It's frustrating every time I see it because I'm pretty sure it's coming from some outside source that you're just trying to shortcut the assignment and you end up wasting way more of your time than you needed to waste. Equals null. This is how we do an empty linked list in CSE116. We're going to set the variable equal to null directly. That means in all of our methods, we're going to have null checks. We're going to check if this dot numbers is null. If that's the way we're representing an empty linked list, we need to check for that. If numbers is null, that means we have an empty linked list. In the case of adding a double, we want to append to the end of the list. We have to do one check. We have to check if numbers is null. If it's null, it's empty, there's nothing there. And what we want to do is effectively initialize numbers. This dot numbers equals a new linked list node with the value we're adding, and next is null. Because this should be, it's empty now. It should be a linked list of size 1 containing the value that we're adding. So this dot numbers equals that one value that we're adding, a linked list of size 1. Else, if we hit the else, that means numbers is not null. We can safely call dot operators and call methods on this. And one of the methods you have is append, which is exactly what we're trying to do. The append method already exists. It's already written for you. We already covered it in lecture, showed you exactly how it works. There's no reason to recreate that method at all. Just call the method. If numbers is not null, call the method that's already available to you and append this new double to the end of the linked list of doubles. It's only when this is null that you have to do some extra work. When it's null, you have to initialize it. But if it's already been initialized, that our numbers already is equal to an object, we can go to that object on the heap and call its methods. In this case, append is the method that does what we want it to do. It's exactly your add ratings method. The only thing that changes, this is add ratings instead of add rating instead of add double, and this is rating instead of double. Everything else is exactly the same. You might want to change your variable name to like R or rating, something that makes sense in that context. But this is exactly the code. There's no reason to change anything. Oh, and linked list node, it's not shortened in the homework. It'll be the whole thing. No reason to not get that one. And the reason for that is I want you to get to the average and the remove rating by a reviewer. I want you to get to those methods. Those are the important ones where you're getting practice going through the linked lists. Like, those are the ones I want you to focus on. The getters, the setters, adding ratings. Those ones are just building up to what I actually want you to be focusing on. What I actually want you to do. Okay, and then let's get to the min method itself. There's a few things here. So one, if the min method shouldn't take any arguments. So then that's the one that we're exposing to everybody who wants to call it. But when we set this up, we're going to want more parameters. So we're going to write a private encapsulated method that's going to help us get the work done, very similar to the add method in a array list, how it had an overloaded method. This isn't strictly overloaded because we used a different name here, but we're going to create a helper method that's going to help us write this thing. The one thing the main method has to do is check if numbers is empty. So if numbers is empty, all your methods should start with this. If my linked list of ratings is empty, then do one thing, otherwise do another thing. And if this list is empty, we're going to return some default value. Negative 1.0 doesn't really make sense in this context, but I wanted to return something that just wasn't confusing. So I'm just going to return some default value. If this were an assignment, I would say explicitly on an empty linked list, the min method should return negative 1.0. Just like in average of ratings, I have a line that says average on an empty linked list should return, I think 0, I said. I don't remember what the value is, but off the top of my head. But I have some explicit value. This is what it should return on an empty list. So that's what you'll hard code for that. And then if the list is not empty, that means we can work with it. And for this, I'm going to do the helper method, which is here because I need to keep track of which node I'm visiting. And this is one of the big differences of working with a linked list instance variable versus being inside the linked list node class itself, is we need to keep track of the node that we're visiting, because with our other algorithms, we kept track of the node we're visiting through the keyword this. But we're inside a linked list of doubles class. In your homework, you're going to be inside the song class. So this is going to be a reference to a song object. And it's going to be the same song object no matter what node you're currently visiting. So this isn't going to, the keyword this, isn't really going to help us here. In this case, it's a reference to the linked list of doubles. We can do this dot numbers and go back to the head of the linked list. But we're not going to be able to traverse the linked list using that keyword this. So we need some way to track the node we're visiting. And with recursion, in general, when you want more information to work with in each stack frame for each recursive call, add them as parameters. This is how recursive calls communicate with other recursive calls, is through parameters and return values, just like any other method, really. So if we want more information that we want to pass to the next stack frame, add it as a parameter. That parameter list you want is not always going to match the parameter list that you have to provide the end user. So we can create helper methods to fix that. I'm going to create a helper method that has the parameters I want, and then from the method that I have to write, because when you're calling a min method, you don't want to worry about what these two extra parameters are. When we're writing the method that we have to have, we're going to have it call the helper method with the initial values for those parameters. In this case, the first node that I want to visit, I'm going to have a parameter to keep track of which node I'm visiting. I'm going to start at the head of the list, which is this.numbers, the instance variable. And I'm also going to track what the minimum value I've found so far is. What's that minimum value I've seen at this point in the list? You could do it without this second parameter. You set things up a little different, but I want to show you more things. I want to show you some options and some tips and tricks and stuff in general. So this one is going to be the min value I've seen so far, and I'm going to initialize that to integer.maxValue. This is the maximum value you can possibly store in an integer. So whatever the first node stores, I know it's going to replace my max value. It has to be less than or equal to integer.max value, because if it was bigger than that, it wouldn't be able to fit in an integer and things just wouldn't work out for me. So I'm initializing this to something that isn't going to interfere with my logic, which is basically the accumulator pattern. Hopefully that much is clear. I'm setting up the accumulator pattern where you learn the accumulator pattern and then you use it to find mins and maxes and stuff. Doing the same thing but with recursion here. So this is my initial value for my accumulator variable, but it's a parameter in my recursion instead of a variable on the stack that's created before my loop. So a little bit different setup, but we're accomplishing the same goal. So we initialize double min equals integer.max value, and we start at the head node. And then in our recursion, no, I missed a click there. Then in our recursion, I was a few slides ahead. I already explained all this slide. God. And then in our recursion, in our recursive step, our helper method, if the node equals null, and this is a little bit different too. Before we were doing checks, if node's next equals null, then we'll make the recursive call. Here we're going to sometimes make recursive calls where node equals null. So a little bit different setup, and again, it's up to you how you want to set this up. On the quiz, it might be one way, it might be the other way. Whether we have recursive calls where node is null or we don't. Here I will have recursive calls where node is null. So I'm not making any null checks before I make my recursive calls because I'm making my null check in each recursive call. So if I've made this recursive call on null, that means I've reached the end of the list. I'm actually one past the end of the list at that point. So I'm just going to return min. If min is the minimum value that I've seen so far, and I've reached the end of the list, that must mean that I've checked every single value in this list, and min is the minimum value of the entire list. So let's just return that up the recursion. It's the append method. It's not in the. I kind of wish I did, but you can still cut and paste it from the linked list node class that's in the examples repo. You can cut and paste it from there into your homework. That's perfectly legal. Any code that I show in lecture or is in the examples repo is always fair game to use. Just cut and paste into your homework assignments. So you can cut and paste that append method in. I think for next semester I'll add it into the handout then. I think it used to be, I must be on removed right now, but I don't know if that makes sense. I'll just give it to you because I want you to get to the last two methods sooner. And then if node is not null, now I can safely say node dot. I can use the dot operator on node because I know it's not going to be null if I ever got into this else statement. So node dot get value less than min, our usual checks for minimum value. If the value at this node is less than the minimum value I've seen so far, make the recursive call on the next node, which might be null. I did not check if next is null, but I'm not using the dot operator on this reference yet because this might be null. Node.getNext might resolve to null. So I can't, like at the top of the method, do node.getValue. That's going to give me a null pointer exception. But node.getNext, I can make this call, which might resolve to null. And then node.getValue, the minimum value I've seen so far must be node.getValue because it's less than min. If node.getValue is not less than min, do the same thing, make the recursive call on next, but with min, the min value I've seen so far instead of value, because value isn't less than min, so min must still be the reigning champion. It's still the minimum value. So it's the accumulator pattern applied to minimum, mins, and maxes like you did in 115, but through recursion over a linked list instead of a loop over a Python list. And each recursive call, we're just returning whatever each recursive call returns. So once we hit the base case, all the recursive calls, no matter how many recursive calls are on the stack, they're all just going to return whatever the base case returned, all the way up the recursion back to the original caller. So this is the example you should, I won't say start with, but as long as you understand the other examples, this is the one that once you understand this one, you're ready to start the homework. Or do what every single student from the beginning of the dawn of time has ever done. Just dive into the homework head first without understanding this example, and then panic when you can't figure out how to do it. Then hopefully you'll come back to this example and understand this example and then go forward. I'm always amazed how many students won't even bother trying to understand this example. They'll just leap into the code. I get it. You just want to get the homework done, but that's going to take more of your time. It's going to take more time. Take the half hour, whatever it's going to take you to sit down and study this and understand this example and then go into the homework. You will spend way less time. I've seen students they'll spend like 5 hours just bashing their head against the homework, trying to figure it out without ever understanding this. I'm not trying to. It is just coming out that way. I think it's a test 3 is where office hour and Piazza volume jumps up, and I'm anticipating that. I think that's part of why it's coming across like that. So I'm trying my hardest to get you to save your time. There's ways to get through this assignment unscathed. And let me say it this way. It's out of frustration of knowing what the pain points are, telling you how to avoid those pain points, and knowing like 20 to 30 of you, probably estimating, are still going to jam yourselves right into those pain points. And it's just frustrating to see. Like, I don't want to see students suffer, as much as some people would disagree with that statement. I don't want to see students suffer. So I try to tell you exactly how to avoid all of that pain and all that wasted time, and the frustration knowing that, knowing that 15 of you are here. Like, most of the class just isn't even going to hear me say it, and then I have to deal with them in office hours, clearly not watching lecture, and then it's just frustrating. And then I have to see the suffering. So I'm trying to get you to avoid the pain points, and then I have to watch you go through the pain points anyway. So I don't mean to come across, especially when anybody who's hearing me say this, none of that frustration applies to you anyway. If you're watching, like 15 of you are watching now, I assume a good number of students will be watching this day of, and watching lecture before, before it's an issue and before you start homework 3, before the homework 3 expected deadline. But there are a good number of students who will not watch this lecture, but will go to my office hours today asking task 3 questions. And that's my frustration on that one. And they'll have new linked list node. I'll see this today in office hours. I would bet large sums of money. Today in office hours, I will see new linked list node of null. I will see that. Here, I'll tell you again. This should never be null. Never, ever, ever in 116 should this first argument of the linked list node constructor ever be null. That's wrong. To represent an empty linked list, we set the variable itself to null, just like is on this example, just like has been on screen for the past 20-30 minutes. But I will see somebody in office hours today with new linked list node null. because there are tutorials out there, because that's what ChatGPT will give you, like wherever that's coming from. I think it's both those cases. And then they're going to ask me to fix it. Yeah, and that's fine. If you're watching ahead, and here's the thing, to distinguish the difference, if you're coming to office hours with a question, if you just mention lecture once, then I know that I didn't explain it well enough, and I got to do a better job explaining it to you. That's way different. But when it's something I emphasize 20 times, you don't reference lecture, and you're like, how come this isn't working? And you have new linked list node of null. Like, my mind's going to go to the worst place. I'm going to assume the worst in that situation. But if you're coming to lecture and struggling with the material, if you just reference lecture one time, hey, in lecture today, I know you said no linked list of null, but I'm having issues with my homework and I got a null pointer exception. I'm super happy to help you then. I'm always happy to help, by the way. Even if I'm frustrated, I'm always happy to help still. The frustration is seeing your frustration. Like, I don't want you to go through that pain. That's the hard part. I'm not frustrated at students. I'm frustrated for students. All right. So deleting a node, this is one that I'm not going to go through the whole algorithm and show you everything, because this is the crux of task 3. This is like the final challenge of task 3 is how to delete a node. But I will show you in theory like what needs to be done to be able to delete a node. And deleting a node, in theory, it's actually pretty straightforward. It's going to be tougher on your homework, and I'll give you some hints right here about it. But to delete a node, say we want to delete this node containing the value 2. To delete that node, we actually need a reference to the node that comes before it. We'll need a reference to this node with the value 3. And what we'll do is manipulate the references of next to be able to bypass that node. So to cut that node out of the list, we're going to say this node that comes before it, its next is now equal to its next. So before the node looks like, the list looks like this. If we do node, say we have a variable named node that has a reference to this node, we do node.next equals node.next. Wait, I lost track. Next, and store a reference to that next's value, which is a reference to this node, in its next. Then we've effectively bypassed this node. We took its next and set its next equal to this node's next, and we've effectively just cut that node out of the linked list completely. So to remove a node from a linked list, we manipulate the references to just get it out of there. Just completely go around that node. So this next no longer refers to this node. This node is effectively not in the list anymore. It still exists. It's still out there in memory, which is fine. But if we go through this linked list, we have 4, next 3, next 1, next null. We've removed 2, so it's deleted from this linked list. And for what it's worth, this node should get garbage collected. Unless somewhere else in memory we have a reference to exactly this node, it's going to get garbage collected and be removed from memory. It's not in the list. It doesn't exist. Nothing in there. So manipulating references. A few other things, but I'll open up the next slide deck because the beginning of the next slide deck has a few... Like, I never fit that in the lecture when that's a Wednesday lecture. So I have deleting a node at the beginning of this. So this would get garbage collected for what it's worth. Not too relevant. Like, I'm never going to test you on that, but this would get garbage collected. And for your homework, there are a few things for this. When you're removing a node from a list, two things we already talked about, so let me revisit those, is what happens when the node you're removing is the last node of the list, which what happens when the node you're removing is the first node of the list. If you have your code set up right, the last node of the list isn't too hard. Just make sure you're doing your check for the reviewer ID before checking for null. So make sure that this node's value is checked. A lot of times you'll be visiting this node and check if its next is null, then shut everything down, but then never actually check this node's value. And we talked about that with the find method, the order of things. That's what I'm talking about there. So make sure that this node is checked, but this node's next, null. If you do the same thing that we did deleting 2, but from 2 deleting 1, 1's next is null, so 2 to delete this node, this next would be null, which is this node's next. Like, the code doesn't actually change. It's just making sure you're checking things in the right order, that this node's value is checked for that reviewer ID. The first node is a little bit different. This one is an edge case that needs to be handled differently because this node's value, a reference to this node is stored in the song class itself as an instance variable. If we're removing this node, then that instance variable needs to refer to the second node in the list to cut this node out of the list. Because if that instance variable is still referring to this node, then we're not cutting out of the list. The only way to cut the head of the list out is to reset that instance variable to the head of the node's next node. So those are 2 edge cases. Well, I don't even know if the last node is an edge case. That would just be a sloppy bug if you're missing that one. Just not paying attention to your code too much, or not seeing that, not noticing it. This one is definitely an edge case. And we have this situation where we need access to 2 nodes. We're kind of looking at 2 nodes at the same time. So we're going through this list, and each time we're checking a node, this one that we're going to delete in this example, each time we're checking a node to see if it needs to be deleted, we need a reference to the node before it in order to actually delete it. So as we're going through this linked list, we need to pay attention to 2 different nodes simultaneously. Or we store one of those nodes in memory, and we look ahead to the next node to see if the next node is something we're going to delete. And of course, null checks are always persistent, always important in these checks. We want to look at the next node. First, we want to make sure next is not null. If next is not null, check its value and see if its value is something we want to delete, and then manipulate the references to delete it. If we don't want to delete the next node, then we can hop over to the next one with another recursive call, look ahead to this one to see if we want to delete it. If we don't, move on to this one, and then we've already checked this value to see if we want to delete it. Its next is null, so we're at the end of the list, and then return and say, well, we got nothing to delete. So those are all my hints for removing a node by reviewer ID. Covers, piggybacking on that kind of ranty speech I just gave. Those are most of the pain points. Those are all the pain points that I can think of right now that students hit on this one. There are always null pointer exceptions. Always, never do dot value or dot get value or dot get next without checking if the node is null first. Make sure you have your null checks. That'll be, like I said, 90% of Office Hour and Piazza questions on task 3 is, what's this null pointer exception business all about? It means you didn't check for null. Whew. Okay. It's only been 5 days, but I forgot how much of a how much it is to lecture for 2.5 hours. Okay, in 25 minutes we don't have much for Stack and Queue, but I also don't have a ton I want to say about Stack and Queue. And spoilers, you're not really assessed on Stack and Queue. So Stack and Queue are very important topics. If for no other reason, interviewers, when you're interviewing for jobs, they love to ask about stacks and queues and data structures in general and algorithms. But stacks and queues come up way too often, in my opinion, on those for what they actually are. Stacks and queues are data structures that limit what. Let me phrase this the right way. Stack and queue, the concepts are extremely important. We've been using stack all semester. The fact that a stack is last in, first out, very important. Idea. Same with queues. The idea of a queue, the concept of a queue. When somebody talks about a queue, you need to understand what these things are. In code, they're less useful, especially stack. I don't think I ever use a stack in my code, the stack data structure, but I will use a linked list and pretend that it's a stack and treat it like a stack. Yes, yeah, in Java, we don't delete anything directly. We just lose all references to it and let it get garbage collected. In C, when you get into 220, you will actually have to manually delete everything. But Java, we don't even have, you can't tell Java, hey, can you garbage collect that for me? It won't even let you. You just lose all references and let the garbage collector do its thing. The same is true with the linked list. If you're done with the linked list, you have a linked list that you created within a code block, for example, or an array list that you created within a code block, and that code block ends, you lose a reference to that array list. That array list gets garbage collected. You don't have to explicitly clean it up or anything. So even when it's entire data structures like that, we don't handle the deletion. We lose all references to it, and then it gets garbage collected. Okay, so let's get on with these. And the whole reason for stack and queue, by the way, let's get our big umbrella over this section of the lecture. Our whole reason for stacks and queues is to limit what you can do with these data structures in order to make sure you're only using efficient operators. For my money, I'd rather say I will just use my data structures efficiently, and then if I want to use an inefficient method on it, I have that option still. If you use the stack in the code, the stack class, you don't have the option to call an inefficient operator anymore. And I'll show you when we get to the code. I'll show you what I mean by that in a little more detail. So stack is our typical last in, first out data structure. I always think of a physical stack of things. You can only add things to the top or remove the top thing, and you can only access the top thing, whatever that thing is, whatever type it might be. Now, physically, yeah, you could pick up this whole pile and grab the bottom thing, but the concept of a stack says no, you can't. You can't even access the second thing. You can't do that. You can only access the top value, the top of the stack. You can only push to the top of the stack and pop off the top of the stack, and that's it. That's all you can do with a stack. That's it. Two things. If it's not one of those two things, you can't do it. There are some implementations of a stack that will give you a third method that's usually top or peak that will return the top element of the stack without removing it. If you just want to look at what the top value is without removing it from the stack. But that doesn't have to exist. It's usually there for developer convenience. A stack in concept, in theory, is just push and pop. That's it. There are a lot of things notably missing here, like size. You can't ask a stack for its size. What are you, crazy? You want to know the size of the stack? You can't do that. Not allowed. Not allowed. Can't do it. Push and pop. That's it. You want to know the size? You keep track of how many times you called push and pop and subtract. You can't ask a stack for its size. So that's why I say just use a different data structure as a stack. You make sure you're only you're enforcing first in, last in, first out. And then you have the option of calling something other than push and pop. But the concept, extremely important. Concept is very, very important. Here's our stack usage. We're going to create a new stack, and we're going to write this stack class in a few slides here. We're going to create a new stack. We're going to push 1. That's going to be the top and bottom of the stack. We're going to push 2, push 3. So our stack has 3 on the top. And then 2 and 1 at this point in time are not accessible. We can only access 3. If we want to access 2, we have to pop 3 and then pop to access 2. And then when we pop, X gets that value 3, and 3 is removed from the stack. So now 2 is the top of the stack. If we call pop, we'll get 2. Pop again, we'll get 1. But we can't access anything other than the top value of a stack. And this is exactly how our stack frames work. We can add stack frames to the top of the stack, the bottom visually in our diagrams. But we can push stack frames to the top of the stack by calling methods. We can pop the top of the stack by returning from the current method, but we can't go from the current method if this is the main stack frame and some method call that we have. When we're in this stack frame, when this stack frame is on the top of the stack, we can't do anything with the main stack frame. We can't access its variables. We can't return from it. We can't do anything in this stack frame until this method returns and is popped off the stack. So same concept, exactly how the stack frame works, how stack frames work. The stack memory is a stack of stack frames, and it does follow the concept of a stack data structure. Push and pop, that's all we get, and then we can mess around inside the top stack frame, access its variables and whatnot. Okay, so here's our stack code for our stack data structure, and we are going to build it using a linked list. So the stack is going to be a linked list, and this also fairly parallels the song class with a linked list of ratings in that we have a class that has a linked list as an instance variable. And then we're going to implement push and pop. That's all we get with a stack. Initialize to the empty to an empty linked list. An empty linked list is a linked list node that's equal to null, not a new linked list node of null null. That is a linked list of size 1 that has the value null. That's not what we want. Not ever in 116. It is just equal null. And then push is going to be prepend. So we could choose which end of the linked list we want to work on. It's much simpler to add to work at the front of the linked list. So when we push, we're going to prepend that node. We're going to prepend to the front, and this is just like the very first linked list example we saw, where we're going to create a new linked list node where its next is the previous head of the linked list, and then set that head equal to the new node. And before we did this in one line, this is the same as this dot top equals new linked list node value this dot top. But I broke it into 2 lines. It makes it hopefully a little more clear. I don't know. But we're going to set the instance variable equal to a new node that has the new value and refers to the old head of the linked list. So we effectively prepended the value, or push to the top of the stack is the way we're thinking of it this time. And then pop, if the top is null, so we always want to check for null before we do any dot operators on something that should store reference to a linked list node. Before we ever do a dot operator on something that should store a linked list node, we want to check it for null. So is the top null? If it's null, we have to decide what to do. In this case, I'm just going to return null. You have a lot of options here. I mean, in general, out there in the world, in 116, this situation won't come up on your homeworks. But I have to decide what to do. A lot of programs will just crash. It'll throw pop off an empty stack exception and crash your program if you don't catch that exception. I'm going to just return null. I need to code something, and that's just what I decided to do. It's the simplest thing to do. Just return null to indicate that the stack was empty. If the top is not null, I get to use my dot operators. So I'm going to get the value at the top. This I do need a temporary variable. I'm going to store that value in a temp variable because that's what I want to return. And then I'm going to remove that node from the top of the stack, which is very similar to how you're going to remove a rating if it's the head of the list, if this is in the song class. This dot top, the instance variable storing your linked list, is going to equal this dot top dot get next. So switch your instance variable from referring to the head of the list to referring to the second node in the list. That's effectively removing the front element, the top element from the stack, or the head element from the linked list, and return that value that we stored in the temp variable. Because once we do this line right here, we no longer have access to that node we deleted. It's going to get garbage collected. We have no reference to it. So we can't go get value on it. So we had to get its value before removing it because we have to return that value. And that's it. That's push and pop. So we're using a linked list and implementing push and pop in our stack class. Now I would just write these two methods, prepend and remove the first element. Well, return the value, whatever I call it. I'd probably just call it pop in the linked list node class, and now I can use my linked list as a stack. But now if at some point in the future I want to call size, I have that option still. With this stack class, I don't have the option to ever call size on my linked list unless maybe I do a getter method to get this this reference and then call size on it. Like I can do something like that maybe. But the point of a stack is to limit you to just efficient operators. And I'm not going to talk too much about runtime, but push and pop are O of 1 operators. These are very efficient algorithms, very extremely fast. Size is not. It's what's called an O of N algorithm. So it's restricting you to just O of 1 operations is the advantage of stack and queue. It's only going to be O of 1 operations, which are constant time, meaning that they'll have the same runtime whether the stack has 3 elements in it, like this one does, or 1 billion. Those push and pop are going to take the same amount of time regardless. Size, you got to hop 1 billion hops throughout memory versus 3. Size is going to be a lot longer to run, a lot less efficient. Okay. So we've pushed 3, 7, and 2. This is what our linked list is going to look like. Top is going to be a reference to 2. That was the last thing that was pushed. We're prepending. So 3, prepend 7, prepend 2. And then we want to push -5. When we push -5, top is now going to be referring to a new node with the value -5. And its next is the old head of the list. And when we prepend, notice nothing in this red box changed at all. Nothing with the old list changed. It still fully exists completely intact. We just have another node that refers to that linked list. And then when we pop off the stack, top, instead of referring to the head of the linked list, we'll get head.next and refer to this node. This is now the new head of the linked list. And we go back to our complete original linked list. And throughout that, nothing in the red box changed. Our original linked list never changed at all when we pushed and popped. This is part of what makes this very efficient, is we're not going through the linked list and making all kinds of changes to it. We're just manipulating the front of the linked list, which is the top of the stack. And then this node would get garbage collected. And how are we doing on time? Not enough time to go into this. I just talked about this a little bit, so I'm going to leave it at that. 250 is where they're really going to talk about runtime. It's like, I want to say a third of the course is runtime analysis. You'll do tons of it. You'll never assessed on runtime in 116, at least not this summer. When we have interviews in the fall and spring, we'll have some interview questions about efficiency when it comes to stack and queue, but summer goes too fast. Something's got to get cut. So queue, first in, first out. We all are familiar with the idea of a queue. You queue up in line, and you queue up at the back of the line, and you dequeue when you get to the front. So we can only add to the back and remove from the front. Those are the only two things we can do. We can't ask this queue for its size. We can't do anything with it. We use enqueue and dequeue instead of push and pop. Enqueue at the end, dequeue at the front. So our example code, we're going to create a queue, which is going to be initially empty, meaning its instance variable is equal to null, not a node with null as its value. The instance variable itself will be null. In Q1, into the back. In Q2 to the back. In Q3 to the back. And then dequeue is going to take from the front. X equals 1, and 1 is removed from the queue, and 2 is the new front of the queue. Okay, so this is similar to a stack, except we have a little bit of difference here because we have to work with both ends of the linked list. We need to a reference to the front and the back. With a stack, we only needed a reference to the top of the stack because we couldn't do anything with the bottom of the stack anyway. But with the queue, we have to work at both ends. Now, adding to the queue, if our front is going to be the head of the linked list, not even the way we think of it. It'll be the head of the linked list because they're singly linked. There is only one head of the linked list. And back is going to be the end where it's a reference to a node where its next is null. It's going to be the last element of the linked list. So we need references to both of them so we can append at the back and then dequeue from the front. So we need two references here. We don't strictly need two references, but to enqueue at the back, we would have to do what we did with add double and what you'll do with add rating is call append, where append will traverse the entire list until it finds a node where next is null and then add the value there. But we can't quite do that with a queue because a queue is designed to be efficient. We need an O of 1 operation for enqueue. So our regular append method is going to have to bounce all over memory a billion times if there's a billion elements. That's going to be way too slow for a queue. The whole purpose of stack and queue implementations are to be efficient. So to get around that, we're going to store a reference to the back of the queue. So when we enqueue, if the back is null, then we just add right there. Easy, same way we added to a stack, same way we did it with the linked list of doubles and everything. The thing's empty. The linked list is empty, so create a new node with the value we're adding. That is the node. And the only difference here is that we need to set front equal to back. So if back is null, front should also be null whenever that's the case. So we want to make sure front is also equal to back because there's only one value in this queue. We want front and back both equal to a reference to a node to that value. And then if back is not null, we already have something in this linked list, and now just set next to a new node. We're going to create a node, add that to the end of the list, and then update back to be that node that we just created, a reference to that node we just created. Dequeue, oops, I'm getting ahead of my slides. I have a bad habit of doing that. Dequeue is going to be similar, but just a little bit different also. If the front is null, return null. We're trying to dequeue from an empty queue, so we're going to return null. If the queue is not empty, we're going to get the front, store that in a temp variable, set the front equal to the front's next. That much is the same as with a stack, is popping off the top of a stack. Same exact thing. There's just one extra check we have to do with a queue, is check if the front is null. If the front is null after, like front was not null, if we removed the front and now it is null, that means we just dequeued the last node, the last element from this queue, which means we need to update back as well to null, because back is still a reference to that node that was just removed, so we want to make sure we update back to also be null. And hey, we are actually going to hit the timing. So with our queue, we create a new queue. Front and back are both equal to null. We're going to enqueue 3. When we do that, both front and back need to be referring to that node that we just created with 3 and next of null. Enqueue 7, now front is going to be a reference to that first node, the head of the queue still, and back will update to a reference to that new node that was just enqueued. And then in queue 2 to the back, we're enqueuing at the back of the queue. Then we're going to dequeue that front node. Front gets pushed down to the next node, and X gets the value of the node that was dequeued. Dequeue again, X gets that value 7, and front goes down the list. These two nodes are garbage collected. Dequeue again, and this is our special case, one of our edge cases, is this node is dequeued, so x gets its value, front will go to its next. Its next is null. So when front is null, we want to make sure that back isn't referring to this node still. We don't want back to be a reference to this, but our typical code is going to still have back referring to this node. So we have to say if front is now null, set back equal to null also. This is where that conditional came in. That's where it kicked in. And we'll dequeue again. This will return null. And a lot of programs, a lot of languages, using their built-in queue and dequeuing from an empty queue or popping from an empty stack is going to throw an exception and crash your program. Ours is trying to avoid that by returning null, but in this specific case, this is kind of just a tidbit of trivia. In this specific case, we actually still do crash, even though we returned null. And we're starting to deal with null a lot, so maybe this is relevant. Null is, there's supposed to be a reference here, but there isn't. That's what null means. Here, this q.dequeue is going to return null and store it in the variable x. X is of type int, which is a primitive. A primitive variable is not expecting a reference. It's not expecting a reference at all. So when I say int x equals null, well, that doesn't make sense at all. It doesn't make sense for a primitive to store null, because null is the lack of a reference. You can't store that in a variable that's not expecting a reference at all. Doesn't make sense. Can't do it. So our program here crashes anyway. So we were trying to avoid crashes returning null, but since this is a primitive, it's going to crash anyway. Which was an accident at first, but I left it in and even added slides to this slide to describe it because that was a nice bit of trivia. It helps understand what null means. Null is the lack of a reference. Primitives are assigned by value, not reference. So it doesn't make sense for a primitive to have null. And we did it. We reached the end with 4 minutes to go. Does anybody have questions on any of that? I'll give it a minute for the stream delay. If not, we just made it halfway through the content of the semester. It's 5 out of 10 lectures done. 50% of the way. Fast. Have I said the summer moves fast yet? Hopefully I said that enough times. This Saturday is the test 1 final. I do fear for those 6 students who haven't even submitted yet. Maybe they'll submit by the end of this deadline and get task 1, but at that point there's no way they're like, I'll already have lectured on task 4 by then. They can't get caught up. They won't be able to. Not that it's not possible, but students who dig themselves, the type of students who dig themselves that hole, they're not going to. They're just not going to catch back up. Is none the same as null, or because Python isn't strongly typed, does it not matter? None is the same as null. Python's not strongly typed, so Python doesn't care what type you store in each variable, but it still does have none as a way to say that there is no reference or value. Like, there's nothing here. It fulfills the same purpose as null. Okay, I rambled enough for the stream delay. We had 1 good question, but no more questions. Means I'm out of here. I'm taking a break. I'll be back for the 11 a.m. lecture. And I'll be back again for 2 p.m. office hours on Zoom. All right, take care, everybody. Have a good one. Good luck with task 3. Let me know if you have questions.